Problem 1. Two infinitely long wires are 2 meters apart from each other. They are both carrying a 3 ampere current in opposite directions. What is the force per unit length on each wire? Please pause the video and attempt this problem. For this problem, we can fairly simply plug our values into this formula right here because we are trying to find force per unit length. Force per unit length is mu sub naught I over 2 pi times I1 I2 over d. Mu sub naught is 4 pi times 10 to the negative 7th Tesla meters per ampere. I1 and I2 were both 3 amperes, and d is 2 meters, giving a net force of 9 times 10 to the negative 7th newtons per meter. Directionally, the wires are carrying current in opposite directions, which means the wires will repel each other. Problem 2. If all 3 wires in this diagram carry the same magnitude of current, rank them by magnitude of force. Please pause the video and attempt this problem. So for this problem, we are not going to use numbers. We are going to try to solve this qualitatively. So remember, in these diagrams, a circle with a dot represents the direction coming out of the page, and a circle with a cross represents the direction going into the page. So wires A and B have currents coming toward us, and wire C has current going away from us. Now let's look at the forces acting on each wire. On wire A, it is being attracted to wire B and being repelled by wire C. For wire B, it's being attracted to A and repelled by C. And on wire C, it is being repelled by A and repelled by B. Now, attracted, repelled, we need to turn that into left and right. So wire A is attracted to B, so it's pulled to the right by wire B, and repelled by C, pushed to the left by C. Wire B is attracted to the left by A and repulsed to the left by C. And C is repulsed to the right by both A and B. So we can say first, the strongest force is going to be on B. On B, both of these other 2 wires are applying a force to the left. B is also as close to the other 2 wires as anything else is. So the total force on B is the strongest. Between A and C, A is pushed to the right by B and to the left by C, whereas C is pushed to the right by both A and B. If these distances are the same, which it looks like they are, that means that the total force on C will be bigger than on A, because those 2 pieces of force work together, whereas for A, they work against each other. So the total ranking should be B is greater than C is greater than A. Problem 3. Find the net force on the rectangular loop. Please pause the video and attempt this problem. So this is a case where we have an infinite wire and a finite wire, or rather 4 sections of finite wire. So we can use this formula where L is the length of the finite section. So let's take them in pieces. First, the top part. Because this current is going to the left and this current is going to the right, it will be a repulsive force, meaning the force on this wire will push the wire downward. We can use the formula F is equal to mu sub naught over 2 pi times I1 times I2 times L divided by D. Plugging in the values, we get 3.6 times 10 to the negative 4th newtons. On this bottom segment of wire, this current and this current are going in the same direction, so it will be an attractive or upward force. However, this segment of wire is farther away. This top segment of wire is 7.5 centimeters or 0.05 meters. This bottom segment is 7.5 centimeters plus an additional 10 centimeters or 17.5 centimeters or 0.175 meters. With this larger distance, the force is smaller. It is 1.54 times 10 to the negative fourth newtons, and it is directed in the opposite direction. So we have the top and the bottom wires. Those were relatively simple. The left and right wires are a little more complicated. Mathematically, we can say that every tiny piece of this wire experiences a force proportional to dl, which means we can integrate. Mu sub naught, I1 and I2 are all constants in our integration, and since we are integrating along this distance, this is the d of our formula, so that becomes our integration value, which means we are integrating dx over x, which integration gives us the natural log. So we can find that the force on this right segment of wire is 7.63 times 10 to the negative fifth newtons. However, that was unnecessary because the right segment and left segment have a symmetry to them. Every point on the right segment has a corresponding point on the left segment that is equally as far from this top wire. Using the right-hand rule, this right segment is pushed to the left, and this left segment is being pushed to the right, which means these two segments will have equal magnitudes of force, opposite directions of force. Their net effect will cancel out, so we don't need them. We only need the force on the top and bottom segments. Again, the force on the top segment was 3.6 times 10 to the negative fourth newtons downward. On the bottom segment, it was 1.54 times 10 to the negative fourth newtons upward. That gives a net force of 2.06 times 10 to the negative fourth newtons directed downward.